Hello, students. This is it, the last section of the book. 14.3, talking about dilations. So dilations are similar to what we've done before. Isometries preserve distance, but dilations do not. Dilations do not preserve distance because we're going to be stretching things out. However, it will preserve angles. Okay, so that's a big piece to understand when you're talking about these kind of the differences, at least the differences we've seen so far. Isometries preserve distance and angles. Dilations preserve angles. So what I want you to think about is isometries are two congruent shapes. So let me put that up here. Isometries make or lead to congruent shapes, whereas dilations lead to similar shapes. Okay, so what we're going to have is we're going to have the idea of kind of stretching something out by a scale factor. And that scale factor is very similar to the relationship with similar triangles, which we called a scale factor as well. So no difference there. We're just going to kind of say, how do I scale it up? So if I scale it up by a factor of 2, everything will be twice as big. Okay. Angles won't be, though. Angles will remain the same. And this is a way that you could take like a rectangle and make the side lengths twice as big, and you could measure the areas and kind of make a nice connection there. All right. Well, let's continue on with 14.3. So again, what you have when you have a dilation, okay, so think about like when you put those drops in your eye, you go to the eye doctor and your pupils will dilate, right? That means they're changing in shape. So a dilation can be bigger or smaller, but what do you have to have? You have to have a point that you're starting from, and then a ratio or a scale factor. Now, one piece to remember is that the scale factor has to be bigger than 0. Okay. So it's possible that your scale factor could be less than 1 and still bigger than 0. For example, your scale factor could be 0.5, which would correspond to a fraction of 1/2. So that if I had the original A, B, C, D, and I used a ratio of 1/2, then I would take the distance from A to O, cut that in half, and that would be my new point. The same is true for B. Find the distance to B, distance to C, distance to D, and I would have this new shape here that would be at a ratio of 1/2 in terms of lengths. But in terms of areas, of course, we would be squaring that. So the area would be 1/4. Okay. So there we go. That's what we've got to have. You have to have a point, because when you're pushing things away or pulling things towards, you have to say from what? What are you pushing it away from or pulling it towards? That's why we have a center point. Okay. And here's the theorem. Under a dilation, the image of a polygon is a similar polygon. So a couple things to remember. The definition of a dilation. So this would be a size transformation. Notationally, I'm going to use the letter S. Size transformation, you have to give me a center point, and you have to give me a scale factor. So you could say 1/2. And then you say, okay, here's my thing, and I get out my new thing. So we have 4 different things that we would be doing. We have a translation. We have a reflection, which I'm going to use the letter F because it's a flip. We have a rotation. I'll use the letter R. And so we have this size transformation, also known as a dilation. So size transformation, translation, rotation, and reflection. Okay. So this is slide, twist, flip, and up here I'm going to say scale, like scale it up or down. Okay, those are the pieces we'll have for our class. All right. So here's construction of a dilation, center O with scale factor of 1/2. I take the shape, I find all of the half distances, which means A prime C prime is half the length of AC. B prime C prime is half the length there. So I end up with side, side, side similarities for triangles, and I know that the original shape and the new one are the same. Next, it says find the image of point P under a dilation with center O and scale factor of 2/3. Again, if you're really looking to do things like this, you can do them on GeoGebra, but you can also practice them here to say if I want to go from O to P, okay, so this is the center, and then I want to go break this line into thirds and say the scale factor is 2/3. So here would be the new P prime. Okay. You can kind of visualize that down here with this image. And it says scale factor 2/3 here. Same thing. You just connect all of the lines and then draw your new shape. Okay. All right, let's take a look at theorem 14.2. A dilation with center of O and a scale factor has the following properties. The image of an angle is an angle congruent to the original angle. So if you have an original and then you do something scale factor wise, you're scaling out the lengths of the edges. The angle between them will not change. And likewise, the image of a line segment is a line segment. It's parallel to the original, but it is R times as long. And I know some of you might think, oh, so it only gets bigger. Remember, R could be any number. So if you have a number 1/2 and you multiply by 1/2, it's going to get shorter. If you have the number 3/2, because that's bigger than 1 when you multiply, it's going to be longer. So it could be bigger or smaller. It really doesn't matter. Okay. Notice here, this is a Cartesian coordinate system because you have kind of the points. When they say a scale factor of 2, what they're saying is look at the original lengths. So the length of the original one went from 4 to 1. So this is 3. Then from 7 all the way down to 1 is 6. So I have a 3 to 6 ratio between small and big. And over here, this length is 2. This length is 4. So I have a 2 to 4 as well. Those are the same. I have a 1/2 for the smaller, or if I flip everything over, I have a 2 to 1 from small to large. It does say ABC is the image. Okay. Remember that, the image. So that's the after. And it's the image of ADE. So ADE is the before. So I started with this one and I went to the other. So we always have new over start, which would be a 6/3, which is a ratio or scale factor of 2. And then all you have to do is this. This is the last piece, which I think is, it's not too bad. But watch. In order to find where the center is, this is what you get to do. Again, like I said, I kind of like this part. Take your point C, that is your new point, and draw a line through the original. So it went through E. Do the same for point B. Point B went through D. Guess what? Where those points intersect is your center. Always. Okay? Always. It has to be. Okay? So that's how you can find the center of a rotation. Sorry, of the center of a dilation. Why I said reflection. So application of dilation, yeah, it's kind of one that if you are interested in drawing things that look realistic, trying to make things that are three-dimensional, we often use what's called perspective drawing. And multiple perspectives are often utilized, and sometimes you have to use more than one. But in order to create this three-dimensional effect, you kind of pick a point in the distance, which we sometimes refer to as a vanishing point, and you create your shape. We'll call it the letter C, and then draw lines from all of the kind of the pieces over to O. And then when you draw your new shape over here, you can kind of use those lines as a guide so that your new shape looks realistic. And let's see here. Let's see here, 2-point perspective drawing. So if you're doing this, you can actually do 2-point perspective drawings where you have like this little city that's drawn here. I have two vanishing points, if you will, and you just kind of extend lines from those. So this is kind of the example I'll show you here. You extend lines from those, and then those lines become kind of what you use to sketch things so that it looks more realistic. And so this here, this one's done in 2-point perspective, 2-point perspective. They all look really nice. Those are very nice. If I click on images, I bet I get some good ones. There we go. But this is kind of what you more want to see, right? If you're kind of looking at something, you know that when you're standing in front of it, the building looks very tall, and things as they go away from you look smaller. And that's where things get a little bit misleading, like in Las Vegas, where things look just as big at the distance. You just have to keep walking. Okay. Is there more? Is there a 3-point perspective? And the answer is yes, there is. A 3-point perspective gives you the idea that things are also disappearing as they go up. So 3-point perspective, there's a YouTube video here on it, allows you to pick 3 vanishing points so that things look much more realistic. Can you go bigger than 3-point perspective? I wonder, can we do 4-point perspective? Yes, you can. And you get beautiful things like MC Escher used to draw. 4-point perspective. And yeah, so this is the idea of 4-point perspective, following the lines and the shapes to make it uh, it's kind of cool. It starts getting a little trippy though. If you want to be, let's see, is there 5-point? How to draw in 5-point perspective. That's cool. Okay, I know there can't be, there is. That is 5-point perspective. So it's like you're in a bubble. Oh, that is cool. And I wonder, I think they've got a 6-point perspective, which is Dick Termes. He was a kind of an artist and also a little bit of a mathematician. He did 6-point perspective. I wonder if they have some of his stuff out here. This is the Termosphere Gallery. Oh my gosh, this guy was amazing. So Termosphere 6-point perspective. It almost looked like you were, let me see if I can find one of his. Termosphere Gallery, is this it? I wonder if it's still active. Yeah, this guy was great. I bought one of his things. He has these little spheres and 1 point, 2 point, 3, 4, 5, and here's 6-point perspective. The 6-point missing from 5-point perspectives. Within the 5, we get all the points of the visual around us. But to get the whole picture, you must add that last vanishing point. You'd have to turn around and look at the room behind you to see the rest of the room. So he actually created these really cool, what are called termospheres, because that's his name, Termis, and it's a sphere. And I don't know if they have any of these as video. Sold, 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 blah, 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 blah. I wonder if they have one that's I don't know, but I'm hoping it'll show you the short video. Okay, here we go. Do you see how as it's twisting, it looks like it's like things are getting closer together or further apart, but they're really not? There's times when I look at these and it looks like I know it's spinning one direction, but it almost looks like I'm turning the other direction. That is that is pretty cool. He did some with like a gallery, where he did some that were like real life. This one is obviously made up. Let's see if I can get back here to his gallery. Man, that is pretty cool, huh? I know. This is a blue mosque. Okay, so he actually traveled to some of these places and then he created them. I thought he did one of like there's the common grounds. I'm gonna go back up. I want to do the mosque one. Why not? Right, let's take a look. Okay, does he? I hope he has the video on it. The blue mosque. Okay, so now. So when he sets these up, it actually self rotates. Wow. See, as you get really close to it. Okay, he's getting really close to it now. Oh, he's actually climbing the stairs. Never mind. That's why he's doing it. So if you look, it rotates. And I can see the globe spinning one direction, but if I really look into it, it looks like it's rotating on the back wall of the sphere going the other direction. Whoa, man, math is so cool. Okay, I'm done. That was fun. So yes, multiple point perspective, a great use of this. Obviously, I got distracted there. I'll make sure it doesn't happen again. All right. What else do we see? Transformations. So if you've ever done anything with cameras, they tend to have lenses that the way it looks on the back, the negative is actually reversed because it's the light goes through the lens and then kind of reflects. But it is a scale image of what you're taking a picture of. So let's see here. Inscribe a square in the semicircle and its given diameter so that two of the vertices of the square are on the semicircle and two are on the diameter. Okay, that seems like a cool problem. Let's see here. Yeah, and the way they solve it is with a dilation. So they find the center point of the circle, and then from there they build a square out that they have, because you can build a square anywhere. And then they say, if I dilate this out, if I just extend this out, right, from here, wherever it hits in terms of kind of these lines, that tells me exactly where the points are for an actual square, because all I'm doing is scaling things up. So dilations can help us solve problems much more quickly. Okay. All right, a couple other pieces. How can we show that a shape that we know is similar, how can we show it using isometries and dilations? And I'm going to tell you, this type of thing is the type of thing that I would put on a test. Maybe not touching at a point, maybe separated, like here's a big one, here's the smaller one. How do I make this one get over there? And so you'd say, oh, well, I'd scale it up, then I rotate it, and then I slide it, or something like that. You would give me a sequence of isometries and dilations to get from one to another. So this, the way that they're showing you kind of in the textbook, the way at least the author or whoever did this one said, is they said, why don't I do a rotation of 180 degrees? And that puts the new shape right here. And then I can scale it up from point A and push it out to get to that new shape. And that is perfect. There's nothing wrong with that. Okay. Is there another way? Yeah, you probably could have. Well, if you want just a single isometry, maybe. But if you had done just if you'd rotated around this point, so now you have the triangle sitting here, you might have then said, okay, now I want to translate it over, or scale it up and then slide it over so that you could get to that same shape and then just kind of slide. So you have options when it comes to these. There's not just one answer. I don't want you to think of that. So especially when it gets to like the question on the test and I give you like two shapes, um, and you'll probably have to do some of everything. Most likely, I'm going to ask you to show me that you understand how to do a flip, a twist, a slide, and a scale factor. I'm going to ask you to do all of those. Maybe you can condense it. Maybe if you use different strategies, you could get to a point where I only need to use 3 of those instead of all 4, but that's up to you. And here's the definition of similar figures. If I can create a sequence of isometries and a dilation, one dilation, then the two figures are similar. And that's where this one ends. It's one of the shorter sections, so I guess we end with kind of that shorter piece. All right, that's it for now. Let me know if you have questions. Off you go.